Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual firmament of 20th century physics, certain moments represent less a gradual dawn than a sudden, blinding flash of insight, reconfiguring the entire landscape of scientific thought. Stephen Hawking's 1973 communication to the journal Nature, titled simply Black Hole Explosions, constitutes such a moment. This concise yet revolutionary paper performed an act of theoretical alchemy, transmuting the accepted image of black holes as eternal, inescapable cosmic prisons into one of dynamic, radiating, and ultimately finite entities. It achieved this by forging a previously unimaginable bridge between the disparate continents of general relativity, quantum mechanics, and thermodynamics. The publication did far more than introduce a new physical phenomenon. It initiated a conceptual earthquake, posing profound questions about the nature of information, entropy, and the ultimate unity of physical law, questions that continue to define the frontiers of theoretical inquiry. To comprehend the paper's impact is to understand how a determined effort to disprove a colleague's bold conjecture led to one of the most seminal discoveries in modern physics. The stage for Hawking's revelation was set against a backdrop of established certainties concerning black holes, objects whose gravitational pull is so immense that, according to Einstein's theory of general relativity, nothing, light included, can escape their grasp. By the early 1970s, a coherent classical picture had emerged, elegantly summarized by John Wheeler's memorable aphorism, "A black hole has no hair." This principle, formalized by the work of Werner Israel, Brandon Carter, and Hawking himself, posited that once a black hole settles into a stable state, it is characterized by mere three properties: its mass, its electric charge, and its angular momentum. All other intricate details of the matter that collapsed to form it are lost, shaved away and radiated as gravitational waves. This elegant simplicity was complemented by the second law of black hole mechanics, formulated by James Bardeen, Carter, and Hawking, which stated that the surface area of a black hole's event horizon, its boundary of escape, could only ever increase or remain constant over time. The parallel with the second law of thermodynamics, which dictates that the total entropy of an isolated system can only increase, was striking and deeply suggestive. Into this established framework stepped Jacob Bekenstein, then a graduate student at Princeton. In 1972, he advanced a proposition that bordered on scientific heresy. He took the analogy between horizon area and entropy literally, proposing that a black hole possesses a genuine, physical entropy directly proportional to the area of its event horizon. This idea was profoundly troubling to many in the theoretical physics community, chief among them Hawking. The logic was inescapable. If an object has entropy, it must also possess a temperature. If it has a temperature, it must radiate energy in the form of a thermal blackbody spectrum, a cornerstone of thermodynamics. This conclusion stood in stark opposition to the very definition of a classical black hole as a perfect absorber that emits nothing. Convinced that Bekenstein's reasoning contained a flaw, Hawking embarked on a rigorous calculation intended to demonstrate its impossibility. He aimed to show how quantum effects, while present, would preserve the black hole's perfect blackness. The outcome of this investigation was a complete inversion of his expectations, and the genesis of his 1973 paper, Black Hole Explosions, unveiled a mechanism of startling originality, born from the turbulent interface of quantum field theory and Girth spacetime. Hawking's analysis focused on the behavior of the quantum vacuum in the immediate vicinity of a black hole's event horizon. According to quantum theory, empty space is a seething foam of activity, where pairs of virtual particles and antiparticles constantly pop into existence before rapidly annihilating each other. Ordinarily, this process has few macroscopic consequences. Near an event horizon, however, the immense tidal forces of the black hole can wrench a virtual pair apart before they have a chance to recombine. One member of the pair, possessing negative energy with respect to a distant observer, can cross the event horizon and fall into the black hole. Its partner, endowed with positive energy, can escape to infinity. To that distant observer, the escaping particle appears as real radiation being emitted from the black hole's vicinity. The infalling negative energy particle, upon being absorbed, effectively reduces the total mass energy of the black hole, in perfect accord with the law of conservation of energy. The conclusion was as beautiful as it was shocking. Black holes are black bodies. They radiate. This thermal emission, forever after known as Hawking radiation, possesses a temperature that is inversely proportional to the black hole's mass. This means larger, More massive black holes are colder and radiate with infinitesimal slowness, while smaller black holes are hotter and radiate much more vigorously. This insight elegantly vindicated Bekenstein's intuition while placing it on a firm mathematical footing. The radiance of a black hole implies it is a dynamic object with a finite lifetime. As it radiates, it loses mass, which causes its temperature to increase, accelerating the rate of radiation. This feedback loop creates a runaway process that, for a black hole of sufficient initial smallness, culminates in a final, violent burst of high-energy particles and gamma rays. The explosion of the paper's title refers to this end stage. Hawking calculated that primordial black holes formed in the early universe with an initial mass comparable to that of a large mountain, roughly 10 to the power of 15 grams, would be reaching the end of their lives and exploding in the present epoch, a tantalizing, as yet unobserved prediction. The 1973 paper did more than solve a puzzle. It erected a new intellectual edifice connecting physics' most fundamental pillars. The formula for the entropy of a black hole, refined by Hawking, became a monument to this unification. The Bekenstein-Hawking entropy is given by the equation stating that the entropy S equals the event horizon area A multiplied by the cube of the speed of light C divided by the product of 4 times the gravitational constant G times the reduced Planck constant h bar. Encoded within this single expression are the defining constants of general relativity G, quantum mechanics h bar, and special relativity C, alongside a concept from thermodynamics S. It is an equation that speaks a universal language, hinting at a deeper, underlying theory of quantum gravity. The initial reception of this idea, however, was one of profound skepticism. When Hawking first presented his findings at a conference at the Rutherford Appleton Laboratory, it met with disbelief. Prominent physicists, including John G. Taylor, were adamant that he had made a mistake. Hawking himself confessed his own shock upon first deriving the result, believing it to be a mathematical artifact. The theory gained solid footing only after independent calculations, most notably those performed by his student Don Page, confirmed his results with greater rigor. Further conceptual support came from the work of Bill Unravel, who demonstrated in 1976 that an observer accelerating through a flat spacetime vacuum would perceive a thermal bath of particles, a phenomenon now called the Unravel effect. This provided a compelling analogue and strengthened the conviction that particle accretion in strong gravitational fields was a genuine physical effect. The legacy of black hole explosions extends far beyond the prediction of a novel astrophysical phenomenon. Its primary, enduring consequence was the unearthing of a deep paradox that has haunted theoretical physics for half a century: the black hole information loss paradox. Hawking's original formulation implied that the outgoing radiation was perfectly thermal. Its spectrum would depend solely on the black hole's mass, charge, and spin, the same 3 hairs of the classical Nair theorem. It would contain absolutely information about the unique composition of the matter that had fallen into form or feed the black hole. A black hole formed from a collapsed star would produce the same radiation as one formed from a collection of encyclopedias of equivalent mass. As the black hole completely evaporates, the information contained within the objects that created it appears to be permanently erased from the universe. This outcome constitutes a severe violation of unitarity, foundational tenet of quantum mechanics, which holds that information about a system's quantum state can be scrambled or hidden, but never truly destroyed. The complete evolution of a physical system should be reversible in principle. The apparent destruction of information by black holes suggested that either general relativity or quantum mechanics, in their current forms, must be incomplete. This paradox became the central driving force in the quest for a theory of quantum gravity. It has spurred decades of intense research, leading to profound new concepts. The holographic principle, championed by Gerard T. Hooft and Leonard Susskind, emerged as a potential resolution, suggesting that all the information contained within a volume of space can be represented as if it were encoded on the boundary of that region, like a 3-dimensional image projected from a 2-dimensional surface. Later, developments in string theory, particularly the work of Andrew Strominger and Kumon Varfa, provided a microscopic accounting for the Bekenstein-Hawking entropy for certain classes of black holes, offering powerful evidence that the thermodynamic properties of black holes are real and derivable from a more fundamental theory. Eventually, after decades of debate, Hawking himself publicly reversed his position in 2004, conceding that information must be preserved, though the precise mechanism by which it escapes remains a topic of vigorous intellectual In the final analysis, Stephen Hawking's 1973 paper stands as a landmark of scientific creativity, a testament to the power of pursuing a theoretical contradiction to its ultimate conclusion. It fundamentally altered our conception of the universe's most enigmatic objects, transforming them from passive gravitational sinks into active thermodynamic participants in the cosmic drama. The brief communication initiated a research program that has shaped the trajectory of fundamental physics, forcing theorists to confront the deep schism between the smooth, deterministic world of Einstein's gravity and the probabilistic, information-preserving realm of the quantum. The questions it raised about the fate of information and the nature of spacetime at its most extreme are the very questions that animate the search for a unified theory today. It demonstrates a beautiful irony of scientific progress that an effort born of skepticism, aimed at dismantling a seemingly fragile idea, could instead reveal the truth about the cosmos of astonishing depth and elegance, forever changing our understanding of space, time, and the ultimate fabric of reality.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.